Okay, in this video we're going to continue with our practice test review. This should say practice test 4. And on this one we'll talk about the calculator permitted questions. Now I don't think a calculator is necessary for all of these problems, but it is permitted for use. Now, I don't have enough room to show my work on the handout here, so I've got a sheet of notebook paper or lined paper to show you how I would approach each of these problems. Number 7, the function f of x equals x squared minus 2 over 7x squared. This should say 7x squared. This function is 1-to-1 on the domain for x values greater than 0. So if it's 1-to-1, then we can find an inverse, and we will do so here, and we will check our answer, so verify our solution. So again, f of x is x squared minus 2 over 7x squared. And the way we establish an inverse is we first rewrite the function as y equals and we will switch the x and the y because the inverse is essentially the opposite of the original function. And after we've rewritten with this new x and y, we'll solve for y by itself. Now, hopefully you've practiced this enough in a variety of different types of equations that you shouldn't have any trouble in doing this. First thing that I'm going to do is multiply both sides by 7y squared, and I now have x times 7y squared equals y squared minus 2. Then I think what I'll do is I'll move all terms that contain y squared to one side of the equation. I think I'll move this y squared to the left. So now I have x times 7y squared, or in other words, 7x y squared, minus y squared equals negative 2. Then I'll treat y squared like a common factor, and I'll factor it out. So I've got y squared times 7x minus 1 equals negative 2. Then I can divide both sides by 7x minus 1. And so now I have negative 2 divided by 7x minus 1. And then finally, take the square root on both sides. And I'm left with the square root of negative 2 divided by 7x minus 1. Now I have to remind you that this y value is not the same as this y value that we started with. These two are not the same. This original one, this y value represented f of x, whereas this y value represents f inverse of x. So we think we found a solution here. We think the inverse of f is equal to the square root of negative 2 over 7x minus 1. But some of you may have been aware here that I did not include my plus and minus sign here, and I did not include it in the final answer. The reason why I didn't include that is because back here we were told that this expression is good for all x values that are greater than 0. That was part of our restriction. We knew that the domain was all x values that are greater than 0. So therefore, when we calculate our inverse, then this is going to be true for all y values that are greater than 0, because the domain of one function becomes the range of the inverse function. And as long as we're talking about y values that are greater than 0, that means that we're talking about y values that are positive, and therefore the positive square root is what we will retain. So I believe that this is our answer for number 7. We think that this is the inverse, so we must check that. And so once we've established this, we will check. And, of course, the way we check this has to be done in two directions. We have to compose f with f inverse at x and show that that ends up equaling x itself. And we must show that f inverse composed with f in that direction also equals x. In order to check, in order to verify that you found an inverse, you must check it in both directions. So in this first direction with the f function on the exterior, we might have something that looks like this. We need, and I'm going to give myself plenty of room to work here, we need something squared minus 2 over 7 times something squared. And so I'm just looking at this f function over here. Anywhere that I see an x, I'm just using a set of parentheses as a placeholder. On the interior of that function f, I'm going to place the inverse that we calculated, which is, in this case, negative 2 over 7x minus 1. And we want the square root of that. So negative 2 over 7x minus 1, and we want the square root of that. And so we would then follow our algebra skills appropriately and simplify this expression in the hopes that it does simplify down to equal x. If that's true, then we move on to the next one. And on the exterior this time, we want the square root of negative 2 over 7 times something minus 1. And the something on the interior here needs to be the original interior function, x squared minus 2 over 7x squared. And again, we'll perform the algebra steps necessary to combine like terms and isolate and simplify with the hopes that we end up equaling x. As long as both end up equaling x, then that would be sufficient to verify that we've identified the correct inverse function. For our next question, we're again dealing with inverses. And this should look familiar since I talked about a problem, it may even have been this exact one, already once in our notes in the past 2 weeks. But we're given an equation that calculates the distance that it takes for somebody to stop a car, the distance based on the rate of speed, r, the value at which they were traveling, and that's equal to this expression here. So in order to establish the speed based on r, sorry, not based on r, but based on d, the distance, well, we would simply find the inverse of this original question or equation. So if the function notation is bothering you a little bit, then we may just write this as distance is equal to 6.95 r minus 90.43. That was the original expression. So now we'll just solve for the other variable and isolate it. Now here's where naming variables is very nice. Instead of using x and y and trying to keep straight which x and which y are we talking about, well, d and r stand for distance and rate, regardless of where they exist in the equation. So we really don't have to rename these functions whatsoever. So I'll add 90.43 to both sides and then divide by 6.95, and ultimately I'll end up with r by itself equal to d plus 90.43. After that was accomplished, we divide by 6.95, and there is our rate based on distance. And we believe that these two functions are inverses for one another. But how do we verify? Well, we've got to check them. So we're going to take the distance function, and we'll call that 6.95 times something minus 90.43. The something ends up being this entire expression. So we'll put d plus 90.43 divided by 6.95. And that's going to be one of our checks. In this case, we're hoping that the expression does simplify down to the variable in question, which in this case is d. We also have to perform our second check, because we can't just check this in one direction, it needs to be checked in both. So we'll set r equal to something plus 90.43 divided by 6.95. And the something on the interior is the other function, d, which was 6.95 r minus 90.43. And here again, as long as this simplifies, in this case down to r, then we'll be happy. And if that's the case in both directions, if both get verified, then we know that the two functions are indeed inverses. We've talked about the benefits of using those individual functions in the past, but now that we have those two functions identified, we can actually answer the question here without using any algebra to solve. So I'll let you do that one on your own. Predict the speed that the car was traveling if the distance required to stop was 350. Well, if I'm trying to calculate the speed, I would use this function. Well, maybe not that one because that's our composed function, but I would use this function since this is the one that calculates the speed, and we know that the distance that was required to stop was 350. So you can go from there and solve the rest of question number 8. Now, for question number 9. This is more of a question about graph transformations than anything, but it's a nice real-world application of such. We're told that the daily profits of a hardware store that sells X gallons of paint are given by this particular equation. Now, that equation is modeled by this graph here. So we've got P of X equals negative 0.05x squared plus 100x minus 2,000. This equation is modeled by this particular graph. Now, the company has an option, they're presented with an option to either pay a flat tax of $18,000 or a tax of 15% on their profits. And the company CFO, their chief financial officer, must decide which tax is, quote, better for the company. Well, if these are the profits, and these key data points kind of tell us what's happening here, if we only sell 20.2 gallons of paint, then there's $0 profit for doing that. If we sell 1,000 gallons of paint, then there's $48,000 worth of profit. And if we sell 1,979 gallons of paint, we're again down to $0 profit. Don't exactly know how that happens, but I assume that the amount of labor and materials that goes into producing this much paint ultimately doesn't net the company any profits. What they would really like to do is sell exactly 1,000 gallons of paint every day. But even if they don't sell 1,000, let's say that they sell 800. Well, if they sell 800 gallons, then their profits are right here, somewhere a little bit less than 48,000. And if they sold 1,200 gallons, well, their profits are about the same. Any data point along this curve tells us what the profits would be based on the number of gallons of paint sold. And we're using this picture here because it's in front of us. We, of course, could have used the equation to go with it. But the transformations associated with this tax, per se, those are going to be a little bit easier to interpret based on the graph rather than the equation itself. Applying the transformation to a graph makes a nice visual representation of what's going to happen. So here we go. If we were to apply a flat tax of $18,000, then what's going to happen is our profit is simply reduced by $18,000. Whatever our profits were at any given number, we simply subtract $18,000 from that, and that's our profit. If we were to choose the 15% tax option, well, what that means is that we get to retain 85% of our profits, and so we could multiply 0.85 times P of X. And if you look at these two expressions, then they certainly do look like some sort of transformation. So what happens in each? I'll use blue ink to represent this first option here, the flat tax of $18,000. Well, since this is a subtraction and it's on the exterior of our grouping symbol, again, I'm not really focused on the equation anymore at all. If this subtraction sign is on the outside of our grouping symbol, well, I know that that is a vertical movement because it's on the outside, and because it's a subtraction, I know that this is a vertical shift. This whole graph, P of X, has to slide down 18,000 units, or $18,000. So if we sell 1,000 gallons of paint, instead of having a profit of 48,000, well, we have to subtract 18,000 off of that after we pay our tax bill. And so this data point is going to drop down 18,000 units to about 30,000 right here. This data point looks kind of nice. That's about 40,000. That's going to drop 18,000 points to $22,000. And that'll get mirrored over here as well. So this data point dropped down 18,000, and this one dropped 18,000. And every other data point along the way is going to drop or be reduced by 18,000. And there ended up being a couple other data points that were fairly obvious. And so if I were to connect these remaining dots to make a smooth and continuous graph, then this blue sketch here, let's see if I can do this on my screen, this blue sketch represents the profits after we pay our taxes, if we were to choose the first option of a flat tax. Now, not too many people are excited about paying taxes, but if this was our option, then we could now establish our new profits based on any X amount, any amount of paint that's being sold. Actually, I think I'll leave those arrows on there so you can see where that came from. All of those data points were shifted down 18,000 units. Now, what about 0.85 times P of X? Well, 0.85 times P of X, that's again a movement on the outside, or a value on the outside. So I know this is a vertical change, but since it's a multiplication, then we're going to stretch, or in this case, compress the graph vertically. And you can call it a stretch too, but anytime that this A value is less than 1, or I should say between 0 and 1, the stretch is going to produce a shorter graph, so we sometimes call that a compression. So it's a vertical stretch or compression by a factor of 0.85. Every Y value gets multiplied by 0.85. And so if I look at the Y values here, 48,000 times 0.85, well, that's going to be 40,800. And our new data point for that position is 40,800. Oh, that's right about here. That's the coordinate 1,000. So we sell 1,000 gallons of paint, but now our take-home or our profit is $40,800. In this case, we had a Y value of 40,000. If we multiply that by 0.85, that's $34,000, and $34,000 is, well, right about here. Oops, up one from there. $34,000. So when we sell, what's this grid line? 600. When we sell 600 gallons of paint, we'll make $34,000 profit. And you can kind of see what's happening here. When we had a profit of $30,000 and paid 15% of taxes, that ends up allowing us to retain $25,500. And what I'm doing is I'm just repeating each of these data points across this vertical, not asymptote, but axis of symmetry. And of course, if we make $0 and we reduce that by 15%, we're still at $0. So that data point ends up being the same. If we were to connect these green data points with a graph, our profit curve looks something like this. Okay, it's not perfect, but it's a good representation of our profit curve anyway. And if I had to choose between the three, well, of course, I would like to maintain maximum profits and not pay any taxes, because it looks like in all cases the red graph was taller, or the Y results were greater in all cases based on X. But the next best option, if we have to pay taxes, if we can't avoid them, it appears that this green graph is a pretty good option. Certainly our income, or our profits I should say, is less than what we had in the red graph, but it's still much larger or higher up on the y-axis than our blue graph is. So when given the option to choose either a 15% tax rate or a flat tax of $18,000, it certainly looks like the best tax option is the 15% tax on profits. And the reason why we would say that is because for all X values, which represents the gallons of paint sold, the profit along that green line is always greater than the $18,000 flat tax option. And you can perform direct analysis there. If we were to sell 1,400 gallons of paint and look at the blue graph, well, there's our profit. If we were to sell 1,400 gallons of paint and look at the green graph, well, there's our profit after paying taxes. This one is always greater for every X value along the way than the profit on the blue graph. And so it's a different kind of way to apply our transformations that we've learned about, but it's also a meaningful one that can be used very easily to illustrate a particular scenario. Now, the questions that you face on the test this coming Friday will be similar in nature, but they may not be exactly the same. So be prepared to utilize inverse functions as necessary and transformations of functions as necessary on the no-calc portion of the test. And you may have to be a little creative in answering your questions, but I think that's a good way to test your understanding of the content so far. If you've got further questions, please let me know. Otherwise, thanks for watching.